pumps have to pump a wide variety of liquids. And you might not know it, but there are many different kinds of pumps that can do the job. This one is known as a hollow rotary disc pump. It uses a rotating disc to create sufficient suction to move thin or thick liquids around. When the pump, here in blue, runs, a hollow disc inside it oscillates. This creates suction, drawing liquid into one side of the pump and pushing it out of the other. Some of the pump's components are cast in sand molds, like this one, for casting the first part of the pump's two-part body. The molten iron takes a few hours to cool and solidify inside the mold cavity. Then, a vibrating machine breaks the sand mold to release the cast part. A computer-guided milling machine finishes the shape. The off-cut pieces of iron go back into the furnace to be melted down for subsequent castings. After it's cast, the second part of the pump's body is machined to its final shape on a computer-guided lathe. The pump's hollow disc, which the lathe machines from a bar of steel, requires a complex cut that only this electric discharge machine can perform. Its cutting tool is a gold wire, charged with a high-voltage current conducted by water. Guided by a computer, the wire erodes the metal in its path, cutting a teardrop-shaped opening in the disc. A laser printer engraves a part and batch number on the finished disc. To assemble the pump, an engineer begins with the first part of the two-part body. Glue is applied to the shaft sleeve, and that's inserted into a channel in the middle. Next, they insert a lantern ring in the same channel from the back. A bearing is then placed on top of the lantern ring. The engineer inserts one more bearing from the other side. Finally, the pump shaft is inserted through all the bearings in the channel. The bearings minimize friction, enabling the shaft to rotate smoothly. Along with this retaining clip, the bearings also prevent the shaft from moving up or down, or shifting side to side with the pump's movement. Engineers then take the second part of the pump's body and glue a bronze plate, called a diaphragm, into a groove at the top. The two parts of the body are then joined together. A gasket is placed in between the parts to prevent leaks. The gasket's made of special paper, like the type used in car engine piping. The two parts of the body are fastened with 10 large bolts, and a heavy-duty steel spring is installed in a groove in the shaft. A steel cap keeps the spring firmly in position. The spring is compressed with a tool, and a bronze stem bushing is inserted. This spring loading is critical because it enables the disc to adapt to thin or thick liquids without clogging or getting damaged. Next, they mount the hollow disc onto the bushing and bolt on the front cover. When the motor turns the pump shaft, the hollow disc oscillates around the diaphragm, which acts as a barrier, separating the suction side of the pump from the discharge side. This plate covers the spot where later the customer will install a safety valve. The oscillating hollow disc produces suction, which pulls liquid through the inlet port, then pushes it out the opposite side through the outlet port. The pump is then spray painted. Next, a metal coupling joint is installed, which is comprised of several parts, including rubber brackets, which make the joint flexible enough to withstand vibration. These parts prevent the connection between the pump and the gear reducer becoming misaligned. The gear reducer lowers the motor speed from 1,800 revolutions per minute to the disc oscillation speed of 300 RPM. Being able to lower the rotation speed is critical, as it enables the pump to move liquids of different viscosities. The disc can also rotate in reverse, allowing liquid to be loaded or unloaded using the same pump. So you could say, The engineering of this powerful pump truly sucks.